Welcome back for our next lecture or discussion in which we're going to take our information from area between curves and knowledge that we learned and apply it. So now we're going to do some examples in which we will find the area between curves. Get some specific functions. And so first we look at find the area between the curves f of x equals the square root of x, g of x equals x on the interval 0 to 4. So here we start out, I'm going to give you an interval in which to find the area over. But a good idea would be to first kind of draw this region out or get a rough idea of what this region looks like. You don't have to. In the next one, we won't. But it's also a good practice if you like to draw pictures. And so here's our plane. The square root of x is half of a sideways parabola starting at 0, 0. Something like that. This is square root of x. G of x equals x. That's a diagonal line through the origin of slope 1. Now, because square root of x is concave down, that means it goes up a little bit at first. And a diagonal line is straight. So that means actually the line x is under the square root of x graph for a brief amount of time. And then at some point, of course, it will go above the square root of x graph. Extending that a little bit here for us. So something maybe like this. And here we're told to find the area between the curves 0, or between these curves on the interval 0 to 4. Now let's look at 0. Both curves are 0. At 4, the square root graph is at the y value 2. At 4, the y equals x graph is, of course, at 4. And so we have a region shaded by these two curves or bounded between them. In fact, we have two kind of portions in which we need to measure. And just like we saw in the last video, it's very important to understand that I can't simply integrate from 0 to 4 because the curves cross here at this point. Before this blue dot, the square root graph is above the x graph. After this blue dot, the x graph is above the square root graph. How do I find this blue dot? That's just an exercise in algebra. You're asking yourself the question, where do they intersect? Remember, that was the first step. Find the bounds and the intersection points. We know the bounds. If they have any intersection points, let's see. We would do that algebraically where they're the same. And so what I will do here is I will take the square root of x and set it equal to x. Solve it. Solve for x. How would I do that? I don't like square roots, so I will square both sides. We get x on this side, x squared on the other. Anytime we have a quadratic, you always like to set it equal to 0. That way you can either factor it or use the quadratic formula. In this case, it factors quite nicely. I'll factor out the x. I have a factored polynomial equals 0. That means one of these factors must be 0, and we get two solutions, 0 and 1. This tells me that these functions intersect at the x value 0, which we already knew from the picture, but if you didn't, now you do. And they also intersect at the x value of 1. And so that tells me here at 1 is that blue dot. When x is 1, that is where they intersect. And in this case, well, it's obviously not to scale. Let's fix that a little bit. Square root graph, we're here at 2. And this blue dot is at 1. Now, again, just ignore the fact that it's really not to scale. But we get the idea. Square root of 1 is 1. And when we plug 1 into g of x, we get 1. And so now we know we're going to have two regions. On 0 to 4, we have to start at 0. We have to stop at 1 because it looks like they might make a switch. We continue at 4 to 4. Now, if I don't have the picture, how would I know which curve is larger, right? Because now I need to measure the line segments in each region. Between 0 and 1 and between 1 and 4. Now, if I look at the picture, it's clear that the square root graph is above x in this region. And the line is above the square root graph in the second region. But if we didn't, we could do this algebraically. So consider the interval 0 to 1, and then the interval 1 to 4. How would I know which curve is larger? Well, larger, just which one has the larger output. And so we will pick a value anywhere between 0 and 1. So test, so let x be 1/2, say. Well, let's look at f of 1/2 compared to g of 1/2 and see which one has the larger output. F of 1/2 will give me the square root of 1/2. G of 1/2 would just be 1/2. If you put this in the calculator, if you don't know, right, if you're not clear on what the square root of 1/2 is, it's less than 0.5. Or sorry, it's larger, my mistake, is larger than 0.5. And so the square root of 1/2 is larger than 1/2. That tells me that f of x, or the square root graph, is above g of x, the x graph. And so that means line segments in this region will be the square root of x minus x. Between 1 and 4, let's let x be 2. You don't have to make 2. Any value between 1 and 4 will do. Let's look at f of 2 compared to g of 2. F of 2 is the square root of 2. G of 2 is 2 itself. Put it in a calculator, you'll see that the square root of 2 is less than 2. And so that means the g function is larger, has a larger output in this region. And that means measuring line segments between 1 and 4 will look like x minus the square root of x. Same function, it's just a different order of subtraction in order to measure the right length of the line segment. So that's how we could do it without even addressing the picture. And now if we want to find the area, we will integrate all of these line segments together. In this case, from 0 to 1 dx, plus, now we'll integrate from 1 to 4. And so in order to find the area of the green shaded region, we have to answer 2 integrals. Now, it's not so hard in terms of work, because in both integrals are the same functions, just written in a different order, so not going to be too difficult. We rewrite it here. And now let's evaluate these antiderivatives. Let's measure this area. And this is where now the fundamental theorem of calculus will come in. So fortunately, it's written right above us. In order to evaluate this definite integral, we just need to know an antiderivative. So we go back to our Calc 1 knowledge, and in this case, we have a way to answer both of these. We'll just use our power rule. Remember, the square root of x is x to the 1/2. And so taking antiderivatives, I get 2/3 x to the 3/2 here. Remember, think of it as x to the 1/2. Add 1 to the exponent and divide by that number. So 1 plus 1/2 is 3/2. Minus x squared divided by 2, or 1/2 x squared. That's the antiderivative for the first functions. Now, fortunately, right, like I said, it's not too much more work because same functions here written in the opposite order. So we have the same antiderivative, just written now 1/2 x squared minus 2/3 x to the 3/2. So we take that antiderivative, and that's not our answer. We evaluate the antiderivative at the endpoints and subtract them. And so in this case, 1 to 4. In this case, 0 to 1. In this case, 1 to 4. And we'll add these two values together. We'll measure this definite integral, we'll measure this one, and add their two values together. So if we plug 1 in, right, it's f of b minus f of a, so top value first. We get 2/3, 1 to the 3/2 is still 1, minus 1/2, 1 squared is 1, minus, plugging in 0, we get 0. And so the first definite integral gives me this number. We'll simplify it in a second. Plugging into the second one now, plugging in 4. Now, okay, we have to be careful. So 4 squared is 16. 16 divided by 2 is 8. Minus x to the 3/2. Now, don't be fooled by the rational exponent. It's just two operations. The denominator is the root, so square root, and then I cube it. So the square root of 4 is 2, and 2 cubed is 8. So this answer is 8. And then 2 divided by 3, so that's 16 over 3. So that's plugging in 4 minus. Now again, we're not plugging in 0 here, we're plugging in 1. So be careful, there's a second value here, minus. Plugging in 1, we get 1/2 minus 2/3. And so my second definite integral will give me this number, this difference. The only thing that remains to do now is to simplify my answer, right? To combine these fractions together and get a number. And so we have 2/3 minus 1/2 plus 8 minus 16/3 minus 1/2. Don't forget to distribute the negative, plus 2/3. And I distribute the minus sign. And so let's combine our thirds for a second. 2/3 negative 16/3 2/3. So 2/3 plus 2/3 is 4/3, and 4 minus 16 is negative 12/3. Oh, but negative 12/3, that's a nice number, is negative 4 plus 8. And then negative 1/2 minus 1/2 is negative 1. So negative 4 plus 8 is 4, minus 1 is 3. In this case, it worked out. We got a nice, cool number answer. It's positive. That's a good sign. And that measures the area between these two curves. And so the area between these two curves is 3. So again, this was an exercise in actually finding the area and using our knowledge from calculus and definite integrals to evaluate it. And so let's get another example. Let's get a little bit more practice in. In this case, I will not give you a region to integrate over. I will just tell you find the area bounded between the curves. And so in this case, it's not like we start with 0 to 4 like the last example. Here, we need to find those intersection points to give us some bounds. We're not given them to begin with. Either way, we need to find intersection points just in case it changes, like we saw in that example, in the region that we're given. But in this case, we're not even given a region. And so we'll just find the naturally bounded region by finding their intersection points where they cross. And so the first thing I will do is I will take x squared plus 1 and set it equal to 2x plus 1 and figure out what the solutions are. What x values are they the same? Where do they cross? So if I subtract everything to the same side, the 1's cancel, and I get x squared minus 2x. We have a quadratic. It factors quite nicely. And I get two solutions. So these curves intersect at x equals 0 and x equals 2. So on the x-axis between 0 and 2, we have places where they cross in the plane. Now again, I'm going to do this without actually ever looking at a picture. This is kind of nice to do, so it doesn't rely on your geometry skills. So right now I'm going to be integrating from 0 to 2. That's one region then. Now all I need to do is figure out which function is larger. So we have one interval, 0 to 2, to consider. Which function is larger? Let's pick a test value. Any value. We'll pick 1. That's right there in the middle of 0 and 2. And I'll plug it into f and g and see which one gives me the larger output. So for the parabola, 1 squared is 1 plus 1 is 2. 2 times 1 is 2, and 2 plus 1 is 3. And so in this case, the line, or g, is larger than the parabola on this interval, 0 to 2. So that means in order to find the length of these straight lines, we will need to subtract g of x minus f of x. G of x is 2x plus 1 minus f of x. Now, it's very important that I put parentheses here because I need to subtract the entire function. If I do not write the parentheses, then what you have done is you've subtracted the first term of the function and then added the other term of the function. And this will give us an incorrect answer. So always be careful with parentheses. Since it is a subtraction, whatever comes after the minus sign needs a parenthesis because you need to make sure you subtract all of whatever's there. Since this function has multiple terms, you need to be careful of that. And so measuring the straight line segments, that's what they would be. I will add up those straight line segments, integrate them together from 0 to 2 as I slide along the x-axis. And so if we distribute that minus sign, 0 to 2, 2x plus 1 minus x squared minus 1. So it looks like the 1's are going to cancel. And we're going to be left with negative x squared plus 2x. I just write the negative x squared first. You don't have to. And now comes again the fundamental theorem of calculus. We need to evaluate this definite integral. So all I would need to do is find an antiderivative and plug in some numbers. I'll use my power rule to get negative x cubed over 3 plus x squared and evaluate this on the interval 0 to 2. So plug in 2 minus plug in 0. Be careful with the minus sign here. When I plug in 2, I get negative 8/3. Plugging in 2 plus 4. And plugging in 0 in this case is going to give me 0. Right? Always be careful. Don't always assume it gives you 0, but again, here it does. And so my answer is negative 8/3 plus 4. If we find the common denominator for 4, that's 12/3. So 4 into thirds would be 12/3. And then we have negative 8 plus 12, which gives me positive 4/3. Again, we got a positive quantity, which is a good sign. And this measures the area between these two curves. So yet again, another example of finding the area between curves. Even if, and this is important, even if we measured it in a slightly different way, and I changed it up, and maybe threw you for a loop, and it was the same question, but now I said, oh, f of y is y squared plus 1, g of y is 2y plus 1, I probably wouldn't want to try to graph this in the plane, not because it's hard, just because we're not used to thinking in terms of horizontal functions or moving along the y-axis. We usually like x as our input, y as our outputs, as opposed to y as our inputs, and x values as our outputs. So we have to turn our head sideways and try and graph these. Now, the beauty of this is nothing would change about this function and about this answer. Why? Because y is just a variable, just like x, and it doesn't matter which way I write it. It's just an unknown. When I come to graph it, it's important, right, because of the orientation, but nothing changes about how I would go about this problem. It's just a different letter in my mind right now, since I'm not graphing it. I would still want to know where these functions are the same, except I'll get y values from 0 and 2. I would still want to know which function is larger on 0 to 2. I still test a y value and get the same outputs. And I would know that g of y is larger than f of y. So I would subtract g of y minus f of y, moving from 0 to 2 along the y-axis, dy. I would have the same exact definite integral. The only difference is it would be moving along the y-axis. So if I set up this definite integral, it would look exactly the same. The only difference is it would be this. And from a calculus standpoint, that is irrelevant because I'll find the antiderivative and I'm going to replace y with numbers. And I will get the same answer. So even if I change it into a y variable, if I'm not graphing it, I don't worry about it, and I can still answer the question. And so this gives us some good practice. This gives us an idea of how we're going to calculate it, and then we go into solving more complicated types of problems in homework and things like that. But this gives you a good start. So we have the foundations of area between curves. We have some good examples of area between curves. And as long as you remember those principles and everything you learned from Calc 1, this section is manageable. Again, remember that all of this is applications of integration. So we're not learning anything new necessarily in terms of calculus. We're just applying what we've already learned to different concepts. In this case, area between curves. So I hope that was helpful. If you have any other questions, please feel free to reach out. Other than that, I'll be talking to you again soon, where we will begin the next section.